Hey everybody, we are entering now our final lecture in this unit that is really about just the language of IB mathematics, and this is an important one where we talk about the Système International des Unités, the SI units. So, how do you convert a given number from days to minutes? These are the kind of questions that we answer when we are working with unit conversion and specifically working within these SI units, or the Système International des Unités. So, we'll start off with a TOK question. I want you to think about this for a moment. Is mathematics a language? In what ways is it like a language? And in what ways is it not? How do you know how long a foot is? How do you know how long a meter is? This is actually a profoundly important topic because this really starts to think about how are we going to communicate mathematics all around the world, and think about why a universal language, especially when we're talking about mathematics, is so super important. Well, to give you an idea of how important it was, let's think back to the 1960s. Now, in 1960, some fancy scientists met for the 11th General Conference on Weights and Measures in Paris. Those crazy cats came up with some measurements that were common for things like mass, length, time, atomic quantities, etc. They really knew how to party. But what they did was super important. They adopted the official name of Système International des Unités, otherwise known in English as SI units. Now, they came up with these base units of measurement. The 7 base units are length, mass, time, electric current, temperature, amount of substance, intensity of light. We have those measurements as being the meter, the kilogram, the second, ampere, Kelvin, mole, and candela. Okay, important things to note here is that amperes is in capital A and Kelvin is a capital K. So that's interesting. We don't even use centigrade, or we don't use Fahrenheit for that measure of temperature. We use Kelvin. Now, the most common base units are your meters, kilograms, and seconds, length, mass, and time. And those are the things that we work with the most, especially when you start getting into physics. Now, if you were starting in chemistry, then obviously you're going to be working a little bit more with these things called moles. Also, in physics and in chem, you'll be working a lot with Kelvin. But for our purposes in this course and in just the general physical world in which you live, length, mass, and time are going to be the most important. Okay. Now, what we also did, or what they also came up with, is found some commonly derived units, and the most commonly derived units would be units for area, in which we use meters squared. For volume, we use meters cubed. For velocity, we write things a little bit differently, and it would be meters per second, but we write it like this: ms -1. Okay, and that -1 is an exponent. So you need to think back to our previous unit where we said, hey, what does that mean when we have a negative exponent? That means that term should go in the denominator. And we read this as meters per second. And now you want to get used to this. We don't write out the fractions. We don't write miles per hour. We would write MIH -1. For kilometers per hour, we write KMH to the -1. Okay, and we'll do the same thing with things like density. Our commonly used measurement for density is going to be in kilograms per meters cubed. Okay, kilograms per meters cubed, that's how we read this. Kilograms per meters cubed. Now, you could also have said kilograms per cubic meter. That's perfectly acceptable, but that per is what tells you what's in the denominator. Okay, so let's look at a couple of examples real quick. We want to calculate the velocity of an object that is traveling 1,000 kilometers in 5 hours. So we want to make sure that we are using the right kind of notation here. We're talking about kilometers per hour, right? The velocity is something that is going to be written out as kilometers per hour or meters per hour, something like that. But it's a division problem, right? It's distance divided by time. 1,000 divided by 5 is 200, but we need to think about what the units are. 200 kilometers per hour, right? Kilometers were in the numerator, so that has a positive exponent, but hours was in the denominator, so that has a negative exponent, and that's how we would write it. 200 kilometers hour to the -1. Okay? Doing the same thing with density. Calculate the density of an object with a mass of 550 grams and a volume of 400 centimeters cubed. So density, we saw this in this example here of kilograms per meters cubed, but we can still write it as grams per meter cubed. The idea here is to recognize what has a positive exponent, and that's my mass. So I recognize here that I have 550 as a positive exponent, so it's going to be in a numerator. But then I have a volume that goes in the denominator, right? That volume in the denominator tells me that I should be dividing. So it's 550 divided by 400. I go to my handy calculator and I end up with 1.375, and we have grams in the numerator, so that has a positive exponent. Centimeters cubed is going to get the negative exponent because that was per centimeters cubed. That was in the denominator. Now you might also be thinking, why not three significant figures? Why not 1.38? Well, this is an exact answer. This was a terminating decimal, and whenever we can give an exact answer on IB papers, it's always preferred. Okay, so if it's not too much to actually write out the terminating decimal to where it actually ends, that's how we want to write it out. You don't need to round to three sig figs. Okay, so now let's talk about some of the other SI prefixes. That's up next. So our most common SI prefixes are shown here in this table, where we really like to look at for the bigger factors, bigger than our base unit. We have kilo, hectare, mega, and giga, and it's a hard G for giga. Don't listen to Doc Brown. It wasn't 1.21 gigawatts. He should have said gigawatts. Drives me crazy every time I watch Back to the Future. And then when we're going small, we have milli, centi, deci, and nano. So we think millimeters, we know those are tiny. Those are smaller than meters, so that means we have to multiply by a factor of 10 to the negative 3. Kilometers, we know that kilometers are longer than regular meters. They are longer by a factor of 1,000, or times 10 to the positive 3. So that's why we have this multiplication factor here. And that multiplication factor is really important because that's going to help us actually convert our units. Okay, what we're going to be always doing is multiplying by our base unit that we are, or our given unit. We're going to multiply by some factor of 10, and it's going to depend on, are we going bigger or are we going to go smaller? Okay, and here the picture doesn't show it very well, but this is division. When you're going from a smaller measure and you're going from the right to the left here on this table, you're going from a smaller unit to a bigger unit, we are actually dividing by 10. Okay, so that seems really interesting, and we'll investigate why that is in just a minute. So from small to big, we are dividing by factors of 10. If, however, we are going from big to small, so we're going from a much larger unit of measurement to something smaller, like kilometers to meters, kilometers to meters, we are going to be multiplying by factors of 10. Now, why is that? That seems really backwards, doesn't it? Well, here's the thing. When you are going from a big unit of measurement to a smaller unit of measurement, there are a lot more of those smaller units of measurement inside that bigger unit. So we actually have to include more units of measurement. So going from big to small, we actually want to multiply, right? There are a lot more meters in 1 kilometer, so we have to make it bigger, or the actual number larger. Okay, so let's go ahead and do some practice with converting these one-dimensional units like this by moving across this table. So we want to make sure we give this in standard form, which we know that's scientific notation from our last lecture. And we're looking at converting 2.8 meters to hectometers. Okay, 2.8 meters to hectometers. I know that hectometers are over here, and they have that abbreviation H. So that means I'm moving from this base SI unit here to this direction. So I actually want to draw those going in this direction so that I can see I'm going to be dividing by 10, but I'm going to be dividing by 10 2 times. So it's like 2.8 divided by 10 squared. Okay, now that's the same thing as dividing it by 100. You may also remember a shortcut that you can plug it into a calculator or use a shortcut to know that just means I'm going to move the decimal 2 places over to the left. Okay, now this is not scientific notation. In order for us to write this in scientific notation, we take a look at that decimal and we say, okay, I want to move it to the right 2 places. Moving to the right 2 places means that is times 10 to the negative 2, and don't forget your units, hectometers. And that's it. Let's go and take a look at another one. Now we have 3,200 seconds to milliseconds. Our abbreviation here, the lowercase m, tells me I'm looking at milliseconds. So I'm starting at seconds, and now I'm moving from the left to the right. I'm going from a bigger unit to a smaller unit. That means I'm going to be multiplying by how many factors of 10? 1, 2, 3. So we multiply by 10 to the third power. Again, you may remember this also as saying I can write it out like this and then just say times 10 to the third power. So that means I'm adding 3 zeros. Now writing this out as a number in scientific notation, my decimal is here. I'm moving now from the right to the left 3, 4, 5, and 6 places. So that's 3.2 times 10 to the 6th milliseconds. Okay? So now we're looking at 5 kilograms to decigrams. Now mass is a little bit weird because the base unit is already multiplied by a factor of 1,000, right? It's times 10 to the third because we're looking at kilograms. So kilograms is all the way over here. You're not starting in the middle. And we look to see how many decimals essentially are we moving over, or what are we multiplying or dividing by. So we are moving from the left to the right. So that means we're going to be multiplying. We're going from a big to a small. 2, 3, 4. 4 spaces. So 5 kilograms times 10 to the fourth. And that's going to give me 50,000. Okay? Now, 50,000, we want to write that as decigrams, right? So what do we have to write with this? Let's go ahead and move that decimal over. 1, 2, 3, 4. So that's 5 times 10 to the fourth. You might think, wait a second, didn't we already just do that? We certainly did. What I'm giving you is a process that works every single time. You are definitely going to be able to find shortcuts, and I encourage you to try and find those shortcuts. Okay? So let's try and apply a shortcut for this instance. We are going now from milligrams to kilograms. So we're going from a small to a big, which means we are going to be dividing, right? So if we're dividing, let's see how many spaces we move over. That's 1, 2, 3, 4, 5, and 6. If I am dividing by 10 to the 6th power, that's the same thing as just automatically moving this decimal over. 1, 2, 3, 4, 5, 6. There's my new decimal place. And that gives me 67.8 kilograms. Now, if we want to write this in our actual our scientific notation, I need to move that decimal over one more spot, and that's 6.78 times 10 kilograms. That is scientific notation. So, a couple of ways that we can apply shortcuts, a couple of ways that we can still use a system that's going to work for us every single time. The choice is yours. Just got to be careful. Now, what about working with these things like derived units? Well, derived units are things like squared units, or maybe cubed units if we're looking at area or volume. And what we can notice here is that something has changed in this conversion table. Now we're going to be multiplying or dividing by 10 squared. Why? Well, we're looking at square units, which means we are looking at area. So I've got meters in one dimension for one length, but then I've also got the width or the height. And to find area, you are working with meters squared. So you have to multiply essentially by both dimensions. So you're not just multiplying by 10, you're multiplying by 10 squared every single time. Okay? So we want to convert each one of these to our stated units. So for this one, 1.5 meters squared to centimeters squared, starting at meters squared, and I'm moving over 10 squared and another 10 squared, which means I'm going to multiply that by 10 to the 4th power. Okay, multiply by 10 to the 4th power. That tells me how many centimeters squared I have. So you can give that in scientific notation. There's your answer. Okay, you could also write this out. 1.5 times 10 to the 4th would be the same thing as 15,000 centimeters squared. If you wanted to write it in notation where you know what those numbers are, you don't have to think about the scientific notation. Okay? Either way is going to work. Now, what about our next one? From 3,240 meters squared to kilometers squared. So now we are starting at meters squared, but we're moving the other direction, which means we have to divide by 10 squared, and another 10 squared. That's 3 10 squareds. So what does that mean we are going to be doing? It's like we are dividing by 10 to the 6. So 3240 times 10 to the -6. That's the same idea as dividing by 10 to the 6th power. It's just one kind of shortcut way you can do it. Okay, well, let's take this and try to write it out. That means we are moving this decimal place over 6 places. So we have 1, 2, 3, 4, and then 2 more, 5, 6, 0, 0, and then finally our decimal. So that's going to give me 0.003240 kilometers squared. Now again, that's a gross number. We don't like to see it like that, so let's go ahead and write it in scientific notation as well. And we can say that's 3.240. I'm adding that extra 0 because that's how precise that we were in the beginning. Okay, and we are saying that is times 10 to the 3 kilometers squared. Either way is acceptable. You can write it like this, the 0.003240 kilometers squared, or 3.24 times 10 to the -3. Now, volume, we are introducing a third dimension, right? We have depth, so we not only have our meters for our base and our height, but then we also have the depth, which means now we are multiplying by an extra factor of 3. Or an extra factor of 10, excuse me. So multiplying or dividing by an extra factor of 10. Let's try a couple of those examples. Convert each measure to the stated unit. Give your answers in standard form. Okay, so we have 0.8 meters cubed. Oh, I don't actually have any conversion there. Let's go ahead and do this to centimeters cubed. Okay, so to go from that direction, we are going from meters to centimeters cubed. 1, 2, and it's that division, so it's like multiplying by negative. So 0.8 times 10 to the how many? Well, I'm moving 2 groups of 10 to the 3. That means I'm moving 6. So 0.8 times 10 to the -6. Okay, and that is centimeters cubed. Now this is almost scientific notation, right? Almost scientific notation. All we need to do is think about this. We want to move the decimal over 1 space to the right. So that's like multiplying by 10. And that gives me 8 times 10 to the -5 centimeters cubed. If you don't believe me, go ahead and check it out by using a calculator. Try and do the full process by moving those decimals around. Okay? Next example, 15,900 centimeters cubed to the decameter. Decameter, that's the DA, and that is moving 1 spot. Oh, I'm sorry, we're starting over at centimeters. We're starting here at centimeters cubed, and we're moving 3 spots. So that's like multiplying now by 10 to the 9. Okay, so we have 15,900 times 10. Oh, I'm sorry, we are not multiplying by 10 to the 9. We are dividing by 10 to the 9. We are going from, again, a smaller unit to a bigger unit. So we are dividing by 10 to the 9. So that's like this, times 10 to the -9. My shortcut that I can apply here is I'm going to think about how many decimal places am I moving this over to get to that scientific notation. And I'm moving it over 4 spaces. If I'm moving it over 4 spaces, that's 1.59 times 10 to the -9 plus 4. And that gives me -5. So shortcut ways that you can work through questions like this. Again, if you need to use the longer system, go ahead and use the longer system. We'll work on more practice with this in class. Okay? Now, a couple of other things to note just to add on to the end here. There are some non-SI units that are generally accepted and readily used, but the conversion factors can be a little bit different. Okay? So, time. Time is one of our big ones. We don't always just look at things in seconds because seconds, depending on Like if you're looking at air travel or car travel or space travel, we don't want to measure things in seconds because the numbers get just astronomically huge real quick. So we will often look at things in minutes, hours, or days. And the conversion factor for those is weird because it's on a base 60, right? So to go from minutes to seconds, multiply by 60. If you're going from seconds, or from hours to seconds, you need to multiply by 60 again. So that's my 3600. And if we're going from seconds to days, right, or from days to seconds, then we need to multiply that 3600 by another 24 hours. So you just got to be careful about how those conversion factors work and whether you're going from small to big or big to small measurement. So for area, we use this thing called a hectare, and a hectare uses the abbreviation HA, and that is equal to 10,000 meters squared. Okay, 10 to the 4 meters squared. Volume, we look at liters. Liters are used as 1 decimeter, 1 decimeter. Okay, mass, we also might look at the metric ton. Now, you guys might think back in your English units of measurements that 1 ton is 2,000 pounds. That is TON, not TONNE. Okay, this is the English ton, is 2,000 pounds. A metric ton is 1,000 kilograms. We call that a metric ton, and that is 1,000 kilograms. Now, these two measurements are actually not that far off. It's only off by about 10% or 200 pounds. That's it. But we do need to make sure we at least understand that 1 ton, using lowercase t, is equal to 1,000 kilograms. Again, usually any time that you would see this on an external assessment for an IB paper, it's something that would be provided for you. At least you would know some of the basics, but you should at least know the basic process of unit conversion. All right, that's it for today. Thanks for watching, guys. Have a wonderful one. I will see you next time.